Okay, welcome back everyone. Today we're gonna code our own read line function. So basically we will do a function that reads one line from the standard input from the keyboard, but with a twist. We will use the select function and make it so that there's a timeout. So you can have like 5 seconds in order to write your name or something like that, and then it times out and reacts to it. And that's not something that the regular scanf or fgetS methods can. So we will use the select function, and that basically it listens for activity on a specific file descriptor or several file descriptors. So if we open a file, it can react when there is something to read from that file. And for the same stuff, it will work with reading from the keyboard. It can also read from a socket, like when you connect to an internet host. You can use select in order to know when there's something that can be read. Anyhow, we will use it to read from the keyboard. So let me just log into my system. Okay, we will create a file called, we will call it TRL, timed read line. So I will put in the header trl.c timed read line, and we will have a couple of includes. First of all, we will include the standard IO as usual, and also the standard library. We will need sys time age in order to make the timeout part, and sys types.age is for select. We will also need the uni standard library, as long as string.age, so we can manipulate strings. Okay, so we will begin by our timed read line function, and yes, and that will be a char function. So this will return this string that has been read from the keyboard, or it will return 0 if it times out. And we will have one argument, which will be the timeout. Okay, so first of all, we will need a buffer that we will read the data to, and that will be a char string. Let's make it 512 characters, and this is the variable that we will be returning, so we have to make it static. Static means that this data will be saved in the memory even after the function returns. So in that way we can use it to return a string value. We will also need a fdset. That is a specific variable type, a structure, for the select function. We will also need a struct timeval, which is for the timeout part of the select function, and a return value for the select function, just a regular int. The first thing we'll do is we will zero this RF RFDS variable, and then we will use the fdset to listen for the standard input 0, like I have put here. 0 is the equivalent of standard input. So we will listen for the standard input and we connect it to our RFDS struct. Then we have to make this timeout part. So we will add the timeout in seconds, and we will use 0 milliseconds. And then we will call our select function and let it return to our ret variable. And this first argument is how many file descriptors we'll be listening for. And that is just one. And then we will send the address of our RFDS variable. And we will send our time val as well. Then we'll check if return has a positive true value, and if so, we will use the fdIs set. So fdIs set is a function or a macro that will check if a specific file descriptor has any data to read from. So we pass in the file descriptor, and that is the standard input, and also the RFDS, the fdset structure. And if it returns true, and if there is any data to be read from our standard input file descriptor, I will zero out our buffer with memset, and then I will use the read function to read from standard input into a buff, and I will read a maximum of 511 characters, so we have one more to go, just to be sure, and send that to the ret variable. And if it ret will be returning the number of bytes read from the read function, and if we return less than 1, that means that it has timed out. No, sorry, that means that it didn't succeed in reading any data. So select was unable to correctly see that. Or it might have read a end of file from the buffer, or from the keyboard rather. Okay, and if that happens, we will return 0, and if we don't, we will decrease the returned number of bytes with 1 and use it as an index to get to the new line at the end of the string, and overwrite that with a 0, so we don't have the new line in our returned string. And then we will return our buffer. And if this if statement is false, so either the select didn't return a positive value, or this macro didn't be true. That means that our timeout happened, and then we will also return 0. Okay, that's basically it. Let's code a proof of concept, kind of the main function. Let's ask the user for a name. What is your name? Think fast. And then we will call our timed read line function with a timeout of 3 seconds. And if name is true, we will print out hello and the name. And if not, we will print out too slow. And then we will exit our program. Let's see if this compiles. So far so good. And then we run the program, and I will answer my first name. It tells back, hello Jonah. But what if we're not fast enough? You see? Too slow. It works perfectly. Alright, then we will look through our code once more. We can use a more command so we can see the code one screen at a time. First we do a lot of includes, and then our function. We will create a buffer with the keyword static so we can return it. We create the FD set that we use for select, and we create a time val for the timeout and a return value. We zero out the RFDS, which is our FD set struct, select struct, and then we bind standard input, which is the 0 file descriptor, to our RFDS using the FD set macro. We set our argument as timeout in the time val, and we set 0 milliseconds. We could improve this function so we can use milliseconds as well if we want to, but for now let's do a 0. Then we call the select, and if it returns true, and if we have any data to be read from the keyboard, then we zero out our buff. We read from the keyboard into buff, and ret will contain the number of bytes read. If that is less than 1, we return 0, and it's less than 1 if read failed, or if it read an end of file. If it is true, then we decrease the return value by 1 in order to use it as an index to reach the new line at the end of the string, and we zero it out, and then we return the buffer. If not, this is if the function timed out, we return 0. And then we have an example code that creates a sharp pointer. We ask for the name and tell them to think fast. We call our timed readline function with a 3-second timeout. And if it returns a string, we will print out hello and the name. And if it times out, we print out too slow. That's all for today. Thanks for watching, and thanks for today.
Okay, welcome everybody, and welcome to today's show. Today we are gonna check under the hood how this command works, or this code rather. If you have been following my C series, this should not really be news to you, what this command does. So, printf hello world. What happens in the operating system, in the CPU, when we issue this command? Printf is a library call. So, the C implementation consists of, on the one hand, all the additional packages that you can install and header files and so on. But in its base, there is a standard C library. It's called libc or glibc, which contains all these functions. And when you look into the man pages, for example, that's when you do man3 and then a command, then you look at the library functions. So, for example, this is the printf man page. But there is one additional level, and that is system calls, or syscalls. And that is basically what we tell the operating system. So printf and other library calls, that is communication between the programmer and the userland software. But then the actual software needs to communicate with the operating system, and that's done via these system calls. So printf, for example, turns into a system call called write, which is used for writing to files, but also for writing to special devices like the standard input and output, like the screen and the keyboard. And then in the next level, the operating system communicates with the CPU, the central processing unit in your computer's hardware. And we're going to take a look at that as well. But let's start with the first level. So we'll create a very simple C program, probably the first one you ever did, a hello world program. And I'm currently using Nano for this. I will probably be using VI when I do the more advanced stuff. But you can use Nano all the way if you don't know VI. Okay, printf, and I usually put in this return 0 line as well. I like structure. Okay, so let's save this one, a.c, and we do gcc, and as expected, it prints hello world to the screen. Okay, no surprises there, but if we don't want to use library calls, perhaps we do this in an educational fashion to learn, or we want to improve the performance of our program. Then we can use the write system call directly. And if we go to the man page, and to access the man page of a system call, you do man2 instead of 3, and then the name of the system call, like write. As we can see, it requires one header file, unistd.h, and it takes 3 arguments, one file descriptor. That is, when you open a file, you get back a special value, which is used to link that file to your other commands. So like you get one of these FDs when you open the file, and then when you write or read to the file, you supply this FD so it knows what files to open or write and read. And then we have a buffer. So that's basically, well, the variable where you want to where the text is located that you want to print in this example. And then a count. How many characters do you want to print to the screen in this case? And then it returns this is an integer value, how many bytes were written to the file descriptor. So not too complicated. Let's create a what should we call it? b.c. That'll be good. And we need the standard input output library, and also this unistd one, like this. And then we do write. And what file descriptor should we use? If we open a file and we want to write to a file, we get that returned to us. But we are not opening a file now, we are writing to the screen. So there are 3 special file descriptors which are always open. And that is 0, which is standard input. That is the keyboard, usually. And then we have standard output, the screen. And then we have one additional one, which is called standard error. And that is usually also the screen, but in a little different fashion, so you will be able to differentiate between these two. But don't worry too much about that. We want to use this second one, with the number 1, so we are writing to the screen. So we put a 1 right here. The second argument is a buffer, so here we put the variable or the text string we want to print. Hello world, new line. And then we need the size of this. So either we count it manually, or we can do something like string length of hello world. But I think I will just put in 5, 10, 11, 12. At least if I spell this correctly. And that's it. So let's return 0. And we compile b.c to b2. And we get hello world. There is a good Linux command that you can use to debug when you're using syscalls, and even when you're not, because there's always a syscall in the background somewhere. You can use strace. So you do strace.f, -f, I mean, and then you type in the name of your binary. And then you get a lot of information, but the interesting thing is this right here. So we see that we sent a write request to file descriptor 1, hello world, and size 12. And then we see the result directly after. So this is a really good way to test your and debug your code. And I just noticed that I started up the wrong binary before. This is the right one. Okay, so now we know what happens at the library level and what happens at the syscall level, the operating system level. What about the CPU? What happens in machine code, so to say? To demonstrate that, it's easiest to do a little assembler, because assembly language is basically machine code. So you send commands directly to the CPU. So let's start a file that we will call abc.asm, and I want to code 32 bits assembly, and we will create a section for data. That's where we store our variables or the data. And then we have a section called text. And here is all the instructions for the CPU. And we start every bit of code with defining the start point, the entry point of the program. And then we put the label right here. Okay, so we're going to start with a real simple code. We're going to do exit 0 in C in assembly. So we're just going to exit our program to begin with. And you do it like this. In the AX register, that is, the registers are like variable space, but in hardware. So you can put one number in each register. And it's a very fast kind of memory. So in the first register, it's called EX. There we decide what system call to use. And I will put a 1 here, which will correspond to the exit system call. In the second, called EBX, we put the first argument to the system call. And as you might remember, let's put a comment here with our write command. So first we have the FD, then we have the buffer, and then we have the size. So into EBX we'll put the 1 for the file descriptor 1. Then in the third register, ECX, we put the buffer. So what do we put here? Well, first we need to create the text string in the data part, and we give it a label. So let's call this string, and we use the db command to put specified bytes directly into the memory. And we'll put hello world, and we can't do the \n in new line because the CPU and the operating system will not evaluate that. However, we can put the hex code for it, and the hex code is A. A. And then I'll put 0 at the end to end the string. But I'm getting a little bit ahead of myself. Let's remove a little bit of this. First I said we're going to do the exit first. So let's begin there. So I'll create a label called exit, and the first system call is exit, as I said. So we put it into EX, and in the first and only argument in the EBX, we put the return code. So every time, it's like the return 0 in C, that closes down the program with a 0 as the return code. And we can specify what we want to have here. So let's put a 5 in there just to notice it. And then we do an interrupt with the hex value 80. That basically says now the operating system should take over and print this to the screen with the help of the central processing unit. So you always fill in these registers, and then you end by int 0x80. Okay, so let's save this, and then I will use NASM to compile this, or to assemble this. And I'm using a 64-bit CPU, so I need to convert it to ELF64. And the name of the file is abc.asm. And now we created an object file, abc.o, which we will just link in to a binary. So ld abc.o, and as output we name it abc. And then we run it, and we don't see anything. But if we add a ampersand at the end and press enter a couple of times, we see the exit code right here. So it works this far. Let's go back into the code and do the write function as well. And the syscall number for write is 4, so we put it right there. And into EBX we put the 1 for the file descriptor. Like this. And into ECX, that is the buffer. And we named our buffer str. So we just put str right here. And then the assembly program will replace the string str with the address to the actual hello world string. And edx should contain the size to write to the screen. And hello is 5, world is 5, there's a space, that's 11 total, and then the new line as well, so 12. And finally we do the interrupt as well. And if we were to have just this, then it would print and then crash, because we always need to exit the program cleanly. So I will keep the exit right here. I will just change the exit code so we see that we can change it as well. And then we save, and we run NASM, we run LD, and we start ABC. Hello world. And if we add the ampersand, we see that it's let's do like this instead. Trace. There we go. Exit 0. And here is our write command as well. So this is what happens on the 3 levels. And if you like this video and you want me to do more videos like this, hit the like and subscribe button and tell me in the comments. And thanks for watching, and thanks for today.
Welcome back everyone, and welcome to today's class. Today we are gonna talk a little bit about an advanced feature of C called function pointers. So a function pointer is just like a regular pointer in C. It's a variable that points to some other part of the memory, but the function pointer, as one can hear by its name, is pointing to another function. And then you can call that variable and it will call the function that it's pointing to. Let's see if we can make this work. I will create a new file called fp, function pointer. And we will include the standard input output, and we will have 4 different mathematical operations. We will have addition, subtraction, division, and multiplication. And these 3 functions will be very similar, and I'm going to do it like this. So I will do void x. This will be the name of the function, but because these functions are very similar, I will make like a what's it called? I don't remember the word currently, but it's when you have something that you have at the beginning and then you copy that up and then you change parts of it. Okay, so we will have 3 different arguments. The first argument will be the target, that is the variable that we want to change, that we want to put the result of the mathematical operation. Then we will have an A value and a B value. like the two values that we want to add together or subtract. And this time I'll do the whole function in one line because it's very similar and quite easy to understand. So I don't have to break it up in different variables and so on as I've done before. Plus, this is the advanced part of the class, so you should know about that. Alright, so I will return, and let's say this is the add. No, I will not return it, by the way. I will do target equals, and then A plus B, for example. Return. Okay. So this is the base function, and I will just copy this up 4 times, and I will call this addition, I will call this subtraction and change the plus to minus, I will call this division and change it to a division sign, and finally I'll call this one multiplication and add the star sign. Okay, so now we have 4 different mathematical functions. Now I will create our main function, and we will have 2 int values. We will have an x and a y, and we will have our function pointer. So our function pointer will be a void and we can call it FP for function pointer, and I think this is the syntax. Maybe we need to alter that a little bit. It was a while ago I did this, but we'll figure it out eventually. We'll learn together. And then we will read from the keyboard. Let's create an operation variable, and we'll do it like this. We'll ask the user, press 1 for addition, 2 for subtraction, 3 for division, 4 for multiplication, and 0 to quit. Something like this. And then we will read the answer into the operation variable, and we will do it like this. Number 1, and we'll do an F. I will create a definition for this F, and it's F flush standard out. So every time I just put an F there, I will flush the buffer. And then we'll read the first number into X, and I will copy these 2. Oops. I will copy these 2 lines and paste them, and number 2 will be read to the Y variable, like this. Okay, now I will do a switch for the operation. So for case 1, that is addition, it's always good when you do a number-based menu like this that you add a comment directly after the case. Either that, or you do something like this. Define addition 1, define subtraction 2, define division 3, and define multiplication 4. Then you can just do case addition. It makes the code a little bit easier to understand. Okay, so if we choose addition, we will point our function pointer towards addition. And we'll break. We'll copy this and we'll do the same for the other ones. And we have subtraction, and we'll point this to subtraction. We have division, we'll point to our division function. And finally, we do have the multiplication. And we'll change our function pointer accordingly. And at the end, we'll put a default statement, which will simply return 0. Okay, I will save this so far so we don't lose it. Okay, so now we want to execute. Now we want to execute our FP, because the FP is currently pointing towards the function that we want to call. So now we'll execute our FP. And we'll do that by something like this, I believe. So basically, the star means that we shouldn't access this variable, but we should access the stuff that this variable is pointing to. And that is the different functions. And then we'll execute that function. And we will give this a couple of arguments. Let's see. Okay, so target A, B. And we need a variable for the results. So the address of result is our target. And the two values are called X and Y. And those will just submit as is, the actual values. So if we have made this correctly, it should call like the division function. It should execute the mathematical operation, and it should store the result in our result variable. So now we'll just print it out. Like this. and we'll quit. So in order to recap, we have 4 different functions: addition, subtraction, division, multiplication. All these functions have 3 arguments: target, A, and B. And they do the mathematical operations and store the results in whatever target's pointing towards, i.e. the variable address that we send to the function. Inside of main, we present a menu for the different mathematical operations. We read 2 numbers from the user, X and Y. We switch according to the mathematical operations, and we use our definitions, our constants, in order to switch. And the only thing we do in each of these is we point the function pointer, this one, towards our different functions. Then we execute whatever the function pointer is pointing towards. We send the address of the result variable, and we send our 2 numbers. And then we'll just print out the results. Hopefully this works, but it might require some tweaking. So let's try to compile FP. Okay. I think it's because we didn't specify the arguments to it. Let's see. So like this, and then int star. Did I do the correct? No, the int star should be in the beginning. So let's try this out. Now we got a little bit closer. 1 single error left. Void value not ignored as it ought to be. Interesting. Probably it's just the parentheses or something like that, which is wrong. Void value not ignored as it should be. Perhaps it should be like this. Maybe just like this. There we go. Now it compiled. Let's see if it works. So press 1 for addition. 5 plus 15 is 20. And 15 minus 6, 9. 9 divided by 3 is 3. 4. So let's do 8 times 8 is 64. And we quit by 0. No, not 0. It does this anyway. Okay. 0. We could fix that, but it's not a huge deal. But it looks a little bit better though. So we'll just take these 4 lines and move them after our switch statements. So if we press 0, it exits immediately, and it still works for the other ones. Okay, so what have we learned today? We have learned how to create a function pointer by taking the name of it with a star in front, parentheses around that, and then another set of parentheses containing all the arguments. We point it like any other variable, but we point it towards the name of our functions. And when we call it, we put the name inside parentheses, and then another set of parentheses and our arguments. Okay, that's all for today. Thanks for watching, and thanks for today.
Hello everyone, and welcome to today's class. Today we are going to talk about this subject, the subject of typecasting. Typecasting, or sometimes it's referred to as just casting, it means that you convert between different variable types. So it can be from a float to an int, or from an int to a float, from a char to an int, or between different types of structures. I'm gonna start by showing you an example so you can see what I am talking about. Let's start by creating a standard C application with standard I/O and a main function. Today I'm using the text editor VI, but you can use Nano or VS Code or whatever you usually do. Okay, so let's create 3 different variables. The first is an int called A, and then I will have a float. Let's do let's do 2 floats. So B and Q for quota. So A equals 15 and B equals 2 and Q equals A divided by B. So it's 15 divided by 2, which will be stored in a float variable. And let's print the result of this calculation. The correct answer should be 7.5. Let's see what we get. So let's do like this. No, not %T. It should be F for a float. And then we will show the Q variable. It just returns 0 like this. Okay, so I will rename this A.C and compile. And the result is 7.5. So what is happening here is something that is called implicit type casting, and that is done by the compiler automatically. So the compiler will take these variables and make this a variable a float implicitly. If we were to specify this explicitly, that's typecasting that we control as a programmer, then we would do like this. Before this a variable, which is an int, we will just put a parenthesis and put float in there. So the type of the variable. This means that during this calculation, this int variable a will be temporarily converted to a float variable, and then the result will be stored as usual in Q. So let's save this one and rename, compile, and we get the same result. So this is the difference between explicit and implicit typecasting. So when do we use one over the other? Well, as long as no piece of information is lost during the calculation, the compiler can handle it as an implicit typecast. But if information might get lost during the transformation, then the compiler will give a warning or an error, and you will have to do an explicit typecasting like this. So basically when you do this, you are telling the compiler, okay, I know the risks and I take responsibility for it. So let's do an example where we might lose some information. What if we were to make all three an int? Let's test that. So Q will be equal to A divided by B, and I will use %f here again just to see the same type of output. I will put Q in there, return 0, like this. And if you wonder why I name it A and rename it, that's an old habit of mine when I'm using VI, so it doesn't recognize that I'm using a .c file, because in some versions of VI it behaves like Vim does and add colors and indentations and stuff like that, and I'm not really fond of that. So this is probably not necessary anymore, but I still do it out of habit. Okay, so this time we get the result 0, and that is probably because we did %f here. Let's try it once again with D for an int. Oh, sorry, I forgot the MB. Okay, now we get 7. So this time we lost information because we didn't get 7.5, we got 7. So it didn't even try to round up the result, it just removed all the decimal numbers. So that is an example of losing information. Another example is when the types of variables are in different size. As you might know, the different types of variables in C use up different amounts of memory. So a char, for instance, is 8 bits. So a string of 8 zeros and ones. And then we have, at the other end, we have something that it's called long int, which is, I believe, 64-bit. And then, in addition to that, almost every other variable type. For example, int and float and double, all are 32 bits. So this one, the char, gives us 256 different combinations. So a char variable can have 256 different values, 0 to 255. And the int and the likes, they go from 0 to, if it's an I need to mention that as well. There are unsigned and signed int, and that means the minus sign. So signed handles negative numbers. So if it's a signed int, then it goes from about 2 billion, minus 2 billion, to plus 2 billion. And if it's unsigned, so it only handles positive numbers, then it goes from 0 to about 4.3 billion. And that's because of the different combinations when you have 32 zeros and ones. Okay, so that was a little theory lesson. Let's create a char called A and an int called B. And we'll let A be equal to 100. You can put characters like an A or a B or an @ sign in a char, but you can also put the numeric value. So anything from 0 to 255. And let's set B equal to A, and then we print out the numeric value of B, which is int. So let's move, let's compile, and let's run. It's equal to 100. So in this case, the compiler does an implicit typecast, because this is smaller than this. So no information is lost. And even if we were to reverse this, so we set B to 100, and A equals to B, so we reverse this, and then we print out the value of the char. We get the same result, because we are still in the range of the char, so no information is lost. But if we take a bigger number, like 300, that won't fit inside of this char, because it only goes to 255. What happens now? Now we get the result 44. And we didn't get any warnings. That probably has to do with the configuration of the compiler, because I believe it should warn or even give an error in this case, because it tries a typecasting silently and it doesn't work as intended, because we want it to be 300, not 44. And this can be quite dangerous. Let's say you are coding an encryption software, and a bug like this gets in the code, and it's silently passed through and might crash the entire encryption or make it possible to hack it. So in this case, I would say you should if this is what you want it to be going to 44, then you should most definitely do a typecasting. Should do int right here. Because then it shows that when you look at the code, then it shows that this is what you intend it to do. And you should try to configure your compiler. Perhaps, let's see, if I remove this and I were to add a flag right here, dash wall, no, okay. Until the next lesson, I will try to find out how you configure your compiler so it behaves as I believe it should, and warn for implicit typecasting in this case. But if you get an error or a warning when you are coding and converting between types, then just add the variable type like this before the ones that you temporarily want to convert. So what have you learned today? You have learned how to use implicit typecasting and explicit typecasting, and how it works and how it should work, and that you always need to be careful and know what you're doing, especially if you code like a server software or something like that. If you want more videos like this, please like and subscribe, and that's all for today. Thanks for watching, and thanks for today. Hello everyone, and welcome to today's class. Today we are going to talk about functions and invoking a function, calling a function. And we are going to check under the hood and learn what really happens when you invoke a function in the operating system, at the CPU level, in assembly code as well as in C code, etc. And why is that information valuable? Well, there are a lot of different things that happens when you invoke a function, and knowing those things will make you a better programmer. Okay, so in order to do this, I have installed a new VPS server that runs on a 32-bit CPU. And that's so it's going to make it a little bit easier for us to disassemble the programs. So let me begin by logging into my new server, like so. And I'm going to show you how to set up the environment. So I begin by logging into as the root user, and this is a Debian machine. So the commands might differ a little bit if you're running Red Hat or SUSE or something else. But if you are running Linux on a server, you probably already knows how to install packages. So basically it's the same. We're going to start by installing the C compiler. So I'll do apt-get update, and then I'm gonna install GCC with apt-get install. And we need a couple of things. I will install GCC and G++, that is the C++ compiler. I will also install make. It's a program that allows us to create small scripts that compiles our code. And we also need the header files, the standard C library. And they keep renaming this, but I think it should be libcdev. So without this, we can't really compile anything. Let's see if I got it right. No errors, that's always a good sign. And I have the GCC command. Okay, we also need to prepare our assembly environment. So I will install NASM, that's our assembler. And we need a linker, the LD command. We probably had this installed already, but in case we don't, or in case you don't, it's inside of the bin utils package. And in addition to that, we also need the GDB, the debugger, and we need objdump, which is a disassembler. So this time it went a little bit faster than last. I have replaced my faulty router. Okay, so now the environment is set up, And I'm also going to I log out from the root shell, but let me just show you one thing. If we just do obj dump like on bin ls, we will get a lot of things that we are not interested in. Yeah, we need the -d as well, because it shows a lot of different things. Besides this, as you can see, this is not the assembly standard that we are used to. As you can see, there is a prefix in front of the register, right here and right here, and in front of regular values you can see a $sign, etc. This is the so-called AT&T assembly standard. The one we are using is called the Intel standard. So we need to add -big M Intel in order to get this standard. So that's one thing. We can also replace this -d with the entire command. So -- and then disassemble equals, and then we can say a specific function like this. Let's wait a little bit with that. But the point that I wanted to make is that the -big M we want all the time. So we can do alias. Let me just see one thing. We can do alias obj dump equals obj dump -big M Intel, like this. So if we do an obj dump now on, for example, bin ls, I always forget this D, so let's put it in there as well. Okay, it works. Great. So then we can edit a file called bashrc with a dot in front of it. And we can put our alias here. That way it will always be accessible even if we log out. So obj dump -big M Intel, no, big M Intel -big D, like this, and save. Okay, now everything is set up. Now I'm gonna start by creating a directory for all this, and I'm gonna create a C file. So let's call this one function.c, and we will just include the stdio, and let us create a function, two functions. We will create a void and we'll call it func1, and this function will call func2, and we will define func2 as well, and this function will just print something on the screen. Hello from func2, like this. And then we'll create a main function which will just invoke func1. And return 0, like this. And I will also put in the function declarations. So void func2 void, and let's copy this down, and we do the same with func1. Okay, so a very simple C file. We have one function which is named func1, and that will call func2, and func2 will just print something on the screen just so it does something. And inside of main we will just call the first function. So this is because we want to compile this one, and then we want to disassemble it. So a disassembler, it takes a executable program file and it shows the assembly code, because everything is assembly, or machine code rather, in the end. So that's why you all should learn assembly language and learn it very well, because then you will have access to the source code basically for every program in the world, at least the assembly version of the source code. Okay, so let's compile this one and just name this A, so I will rename it function.c. We run it through GCC. Okay, have a typo on line 15 in main. Okay, so this should go away like this, and it compiles. And if we try to run this one, we get the message hello from func2. Okay, so let's dig into the assembly code for this function or program. So we run our objdump, which is prepared, so we just run the objdump command followed by a program file like this function. So we run it against the binary executable program file, not the source code. And we get some output. Let's check if we can use this disassemble equals main. There we go. Okay, so here is our main. Okay, it's a couple of instructions. We have a push and a move, and we have a call somewhere, and we have a call to func1, and then we move 0 into the EX, and we get out of the function. So basically, these 3 lines is not related to the function call. This is just ending the main function in the program. So this call, that is obviously part of it, and this call, however, is not. That is because we are inside of the main. I think it's better to show one of the functions instead of main, because that will be a little bit cleaner. Main is a little bit special because it's the main program function. But if we do the same with func1, for example, that should give us a little bit less input. Okay, we still get this weird call. Where does it go? 11E8. 11E8. So it basically jumps to 11. Where was it? 11E8. Is it possible to do disassemble 11E8? No. We could run it through GDB. Sure, why not? So this is the GNU debugger. We can use this program to debug our code and check values of registers and part of the memory, and step through our lines of code, etc. But I want just to disassemble func1. Disassemble func1. Here we go. Oh, I don't remember all this color. That's a bit annoying. Anyhow, so this call here, it's still to 11E8. We can do, let's try disassemble 11E8, see what happens. No. But we can use the X command. The X command is used for checking what's inside a specific memory address or symbol. So we can do X and 11E8, for example, but that won't show us all that much. However, okay, let's do the whole 32-bit register. However, if we add a slash afterwards, then we can give more information about what we're looking for. We can, for example, do BX to get a byte of hexadecimal characters. We can do S to get a string, but I want to get an instruction, so I will do X/I. And then I paste in 11E8. Okay, so this is the register. This is the instruction, rather. So get PC thunk AX. Move ESP EX. Okay, so it basically just moves something off the stack towards the EX register. Maybe some kind of optimization or something like that. So let's not worry too much about this. I think we should focus our energy on the middle part. So, and this too though, but for the call is the most important one. That's what actually calls the function and jumps over to that instruction where the function is. And this stuff with regards to the ESP, that's the stack pointer, this is preparing the stack. We need to kind of emulate how the stack looks like for each and every function in order to make those variables local. So now I think it's time to go over to a little bit of assembly code, and we're going to try out how we may call a function. We'll start with the easiest possible way, and we'll work our way up to this, so we know why we need the different parts of it. Okay, so I will create a new file which I will call what should we call this one? Let's call it call. So call.asm, and the bits will be 32. We will have a global exported symbol called start. We will have a section called data and a section called text. And as you remember, the data segment is what it sounds like. The data segment, that's where we keep our variables and our data. And the text segment is all the instructions, the assembly instructions. So this is where we will start our program, and we will make this quite easy. First of all, I just want a couple of instructions, so this part of the code does something. And I will zero out a couple of registers. So into EX, I will put a 0 byte, or a 0 double word rather. And I will paste this a couple of times, and I will do the same for EBX, ECX, EDX. And let's put a nope. And a nope is a no operation. That is an instruction that just goes to the next CPU cycle without really doing anything. Okay, so now we have a couple of instructions. Now I want to create a function, a very basic function that prints a static text on the screen. So let's begin by creating a label called str for string, and I will just put something like hello, and after that we will have a 0. No, we will have a new line, and then a 0 byte, like this. And we also need to have an address. No, a size. So let's put it here as well as a variable. So str size, and that should not be a byte. We did dB here. The B is for 1 byte, so it takes 1 byte at a time. But this should be the entire register size, so that's 32 bits. And that's why we do D, I think, double word. And let's just put a 0 here for now, anyway. Okay. Or let's put the real one instead. Okay, so the size of this string is hello, it's 5, and then a new line, and the 0 byte doesn't count, so we'll put 6 into this part of the memory. Okay, so we will call our function print, so I'll just do print like this. And if you watch the last episode, you know how to print something. What we do is into EX we put the value 4, and that's the 4th system call, which is write. And into EBX we'll put a 1, and that's for the standard output. Into ECX we should put the string, or the address to the string. So we'll replace this by the label str. But how do we do with the last register, the EDX register? We want to put the actual size of the string, length of the string, and we have that here inside of the str size. But if we were to do like this, str size, what do we put inside of the EDX register? Well, it's not the 6, it's the address that this str size points to. And that's no trouble in the case of the string, because it expects a pointer there. But as this third argument, it wants the actual primitive value. So how do we do this? How do we, if we have a label or a memory address, how do we go into that address and grab a specific value? Well, we can do like this. We can utilize another register, for example, EDX, EX, EVX, ECX, EDX, and we should, wait a minute, let me just check real quick. If we do GDB on the function, and we put a breakpoint at start, and we run it. If we do IR, that's the command info registers, we will get information about all the registers. So these are the names of the different registers. These are the values. So we've used EX, ECX, EBX, EDX. We don't want to use the ESP because that's a stack pointer. EBP is the saved stack pointer. The ESI, that one we can use. Because we need a temporary register to put the address. So let's put into the ESI register, we put the address of str size, and into the EDX we put ESI. So we copy from ESI to EDX, but we don't just put ESI like this, because then we would do the same thing. We would copy the address. Instead, we put this into brackets. So this means that we are not copying the contents of the ESI register. We are using that as a pointer, as a memory address, and we grab the actual value that it points to. And that's what we put into the EDX register. And then we will just do the interrupt like this. Okay, so now we have our first print function done. And how do we call this one? Well, let's say somewhere in the middle of all these instructions, we will just use the jump instruction. So we jump towards print. That means that we are changing the instruction pointer, so we will evaluate this instruction next. So we jump towards it. And that should work, right? So let's just create an exit as well. And here we will just do move into EX a 1 and move into EBX. We can do it like this, XOR EBX, EBX. That means that we run an XOR operation with EBX against EBX, and that always results in zeroing out EBX. So this is a more effective way of putting a 0 inside of a register, because the move might be kind of expensive CPU-wise. And then we will do an interrupt like this. So we will quit with an exit 0. Okay, we say this one, we do NASM, and before we did ELF64, and that's perhaps what you should do if you're running a 64-bit system. But now I am not. I'm running a 32-bit system. So I will just do ELF this time. And then we will do call.asm, which should create the .o, and then we'll link it by ld call o dash o and call, like this. And we run the program, and it prints out hello on the screen. No problem there. But the program exited directly afterwards. And if we go to our code. Let me do a one-liner out of this, by the way. So we do the n-asm, and if that succeeds, we will do ld call.o-o call, like this. So we save a little bit of time. Now I will go back to the code, call.asm, because, okay, it works. We are jumping to this function, but we don't have any way to go back. So we jump to it, but then what? We still need to go back somehow. And how do we do that? Well, we need to have the address of the, when we do the jump, we want to go back here, right? After the function has returned. So we need to get the memory address of this next instruction. And as I mentioned before, that is saved into the EIP register that always points to the next instruction. But where do we save that? We need to put it somewhere that we can use it later on inside of this function. Well, let's use the data segment just like before. So we will create a label called return address, and we will not put anything. We could do like this, that we put a whole 32 bits 0 like this, and that is all well and perfectly fine. But we don't really need to put anything here. What we want to do is reserve that space so we can put something there at runtime. And there is an instruction, instead of dd, we may use resd. So we reserve 32 bits like this. This means that we reserve 1 unit of 32 bits. And if we wanted, for example, 16 bytes, we could do resd2 or resb16, for example. So that would be 16 bytes of data that we reserve space for. Okay, but resd1 should be fine. And before we do this jump, let's move into ESI the address of the return address, like this. And let's see what happens if we just move into the contents of ESI, that is the return address on the data segment, and we will put the EIP. However, when we execute this instruction will be what EIP points towards. So if we jump to that, it will be an endless loop. So we need to put the EIP plus the size of this instruction. So how big is this? It's quite easy to check. Yeah, let's do an obj dump on this one after we have saved. So let's save this and let's do an ASM. What did it say? Warning, uninitialized space declared in non-B. Okay, it wants it in the BSS section, but that's really not error symbol EIP not defined. So we don't have access to the instruction pointer. I think there is an as a macro that we can use to grab the current instructions address. What if we, instead of EIP, were to put a $sign here? Error operation size not specified, okay? When we don't specify a size, we can do move byte and something that will move 1 byte of data. But if we don't do that, then the assembler will interpret from the argument. So in some cases, like in these cases, we move a 0 into a 32-bit register, for example. ECX is a 32-bit register. So then it knows that it's a double word. So this instruction is really D word. But a double word is 32 bits, by the way. But it doesn't seem that it's able to figure that out in this case. So let's put the D word here, like this. And try again. Okay, the warning is still there, but it looks like it went through. Let's do an Abishdam on our call. And we are inside of start. So let's add -- disassemble equals start. And here we just get the start. Very nifty. Okay, so here is the move of the D word, and we move from this memory address that's right. So into the contents of ESI, we move this address. Okay, so it ends in 9010, and 9010 is this exact same instruction. So we can't really use that and return to this one, because then we would do an endless loop again. Instead, we want it to point towards the next one after the jump. So it should be 9018. So let's add 8 to the calculation. So instead of just $sign here, we should be able to do $sign plus 8. Let's try it again. Okay, so this time it's 9018, and 9018 is the correct, no, it's jump, oh, it's the right one. So this is the instruction, the next instruction after the jump. This is where we want to return to. Okay, so it seems to be working. Let's go back and finish this off. So call.asm. So we put the address into the ESI, and then we use it to write to this part of the data segment. Great. And then we jump to our print. We do the whole print operation, and then what? If we don't put anything here, we will do the exit right after. And in this specific case, that's no problem because it exits and we want to exit. But what if we wanted to call this function twice? So in that case, we would take these three and do them twice, like this, no? Like this. Okay, so would this work? What happens if we do this at the current time? We want it to print the message twice and then exit. Let's see what happens. It just printed once. And it's important that you understand why. Because we have the same instructions. We jump towards print, we jump towards print. But the print doesn't jump back. We execute the print instruction and then we don't do anything, which means it will continue on to the exit function and exit the program. Okay, so how do we return to our how do we return to the function call, basically? Well, on the data segment, we did save the address, the return address. So we need to access that. Let's once again utilize the ESI register temporarily. And into ESI, we will move the return address like this. And then we will just jump back into it like this. So in ESI, we put the return address, and ESI with brackets around will be the actual return address, and jumping towards it would, in the first case, go here to the move instruction. Let's save and let's assemble the code and run it. Okay, interesting. We do get an infinite loop this time. And why is that? So first we jump to the print, then we move back towards this instruction, then we do the same thing once again, and we jump to print. Sure enough. And what if we were to do the same with exit? So we put the return address, which is really not necessary, but let's do it anyway. And then we will jump to exit. And we run NASM, and we run our code. Okay, this time it works. So we have created our own way of calling functions. But how does that correspond to how it's done for real? Let's go back to the code. Basically, it works the same way. It won't save the return address in the data segment, so we can remove this right here, and we can remove that part of the code. So those two, and those two, and those two. And let's change the jumps to call instead. And what is the difference? Well, basically it's the same thing. It jumps to another part of your program, but call does something additionally. What it does is it pushes the EIP to the stack. So it saves the return address on the stack when we do call, and then it jumps. So we can remove that part of the code, that's this one. And how do we return from the function then? Well, there is one instruction, which is just return. So call will push the return address from EIP to the stack, save it in memory. Then it will jump to the print, and it runs through all the code in the function, and then it returns from the function. We can add a return here as well, but since this exits the program, it's not really necessary, but it looks better. Okay, so if we have done this correctly, then we don't need anything else. If we run this code, it should print the message twice and then exit. Let's see if it holds up. It compiles, no warning. And if we run call, it prints the hello twice and then it exits out. Okay, so now we have gone through everything related to calling the function, returning from the function, and handling the return address. I hope you enjoyed it. Don't forget to subscribe so you know when the next episode airs, and to get more content like this. Thanks for watching, and thanks for today.